Okay, so right now we've come through 5.1 where we learned what a general antiderivative is, that there are times we might be interested in a specific antiderivative as long as I give you some piece of given information on the original function that you would be able to work backwards. We've learned the basic derivative rules, which is if I give you as an integrand a known derivative, you should be able to work backwards because you've memorized the rules. And then we looked at several basic cases of working backwards where you had power rule that you were undoing. And so we've kind of just been working on the idea of when I give you an integral to complete or to integrate, that your job was to recognize what known derivative you had, and then you were able to work backwards from that to the original function. And so what we want to do here is we're going to start looking at more complicated derivatives where we have been invoking or using possibly the chain rule. And we're actually, I know it seems kind of odd, when we went through the derivative rules, we did product rule and then quotient rule before we did chain rule. But it actually is a little easier to work backwards when there's a chain rule problem as opposed to when there is a product rule or a quotient rule. So we're actually going to work on coming backwards from the chain rule. So this section 5.5, it's called integration by use substitution and pattern recognition. So they kind of go together. The pattern recognition is what we're doing, that we're recognizing that there was chain rule involved in the derivative, that we have this idea that when I go to take the derivative of something that had a composition, f of g of x, that when I took that derivative, what I ended up with was an outside function where I took its derivative and I left the stuff inside, and then we unpacked the stuff by taking the derivative of the inside last. So you kind of came along and said, oh, I'm going to take the derivative of the outside and not worry about what's in here, and then we unpacked it. We took the derivative of the inside and then unpacked it with the derivative of the inside function. So that's just reminding you of what the chain rule is. So now kind of our job is going to be, if you were given this piece as an integrand in an integral, then we want you to be able to work backwards, that if you see this dx, that you would know that you are integrating the derivative of a composition, and so you should be able to work back to your f of g of x. So kind of the idea here is whether I call it use substitution or pattern recognition, you want to be able to recognize that there was a chain rule problem. Like, for example, let's take a look at this. This is a classic chain rule problem. We have all of this stuff on the inside, and so we know that when we go to take the derivative, we first go, what's the derivative of tangent? The derivative of tangent is secant squared. We leave the stuff in the box, e to the 4x squared, but then we unpack it and we follow with the derivative of that stuff. The derivative of an e function is itself, and notice that that itself had a smaller box inside, and then we unpack its derivative. The derivative of 4x squared is 8x. And so the idea is that we work forwards. We take the outermost function and we take its derivative, and then we unpack each box and take its derivative, and then we unpack and we take its derivative until we have nothing else to unpack. And so when we see something like this, what we're recognizing is that everything over here was as a result of chain rule. So now we have to kind of train our brain to recognize when we see something like this that there must have been some unpacking, that we want to see those relationships of what's there. So when you take a look at, say, the problem down here, example 2, which is directly related to this, as you scan through here, what you see is that you've got a lot of stuff going on. But then I see this secant squared right here, and I'm like, oh, secant squared, that is something that I know as a derivative. It's the derivative of a tangent. And then I look and I see that I've got stuff inside of the secant. So when I see that, I think to myself, well, this might have been a chain rule problem. And what I want to see is, once I identify that this is my main function right here, my f of, well, actually it would be f prime, that then I look at what's here, and this must be my g of x, and what I'm trying to check is to see if all the rest of this stuff is going to be my g prime of x, and then of course the dx that goes with that. So that's kind of the idea of pattern recognition. So and a lot of times when we do this, we call this U sub or pattern recognition, because what you're doing is you're recognizing that this is your derivative, known derivative. So you kind of go, I'm going to let u equal e to the 4x squared. That's your quote-unquote g of x, okay? Then we go ahead, and because we know what's on the outside should be the derivative of that, we take the derivative of u with respect to x. And then so we, all right, well, what is that going to look like? It's going to be e to the 4x squared times the derivative of 4x squared, 8x. And then so I then look at this, and we always translate this into differential form. And to be honest, at this point I kind of get into the habit of I always just automatically put it in differential form. So you recognize where your g of x is, or your u. You take its derivative and put it in differential form so that we can then compare it to what we have over here. And if x, 8x, e to the 4x squared, and then of course this dx over here, if that is our du, what we're basically doing is then packing it back up. We're recognizing that what we're actually integrating is going to be secant squared, your outside function, of u, and then all of this stuff underlined in pink is du. So you kind of remove the clutter that happened because of the chain rule unpacking and ignore it, and then just simply integrate the outside function. The antiderivative of secant squared is going to be tangent of u, but now remember, whenever we use a u substitution, you start with a u substitution to make it easier to do, but then you have to always come back in and finish by putting back in the original variable. So we would have tangent of e to the 4x squared. Now I will say that a lot of times when we're doing a problem like this, and I'm doing this as a pattern recognition, I don't necessarily write what's here for the u down. A lot of times I'm simply going to recognize this part in my head. I'm just going to go, hey, this looks like a chain rule problem. So I check that the inside has the derivative on the outside, and then I pretty much just ignore it and go straight over to the answer from that, because you kind of know that the chain rule stuff gets packed back up. So what we're doing is we're basically thinking of composite functions, thinking of it as a single function that is like a box and has other functions inside of it. And when you take the derivative of these functions, you unpack the boxes, you unpack the derivatives of each of the boxes. And then when you go in reverse, once you recognize that all the extra stuff sitting out is from chain rule and needs to go back in the box, you pretty much ignore those portions of it. Like, I'm pretty much taking this portion and kind of saying, oh, that's the stuff that gets packed away again. So I can ignore it and simply focus on the antiderivative of secant squared, which is tangent, and just bring the stuff back along with me. All right? And so the idea is that when we're packing it back up, we're keeping this in mind, that the derivative of f of g of x is f prime, and then you have the stuff that got unpacked from the inside function. And so when we work backwards, you take the stuff that got unpacked and you kind of ignore it because you're putting it back in, and then you know what your antiderivative of f prime would give me back to f. All right? So in the next little section here, this just formally states that what we want to do, if I want to integrate and I have a function of g of x, and I notice that what's in here has a derivative out here, then this is the result of chain rule. And so when I pack it back up, I ignore it, and all I have to do is integrate the function here. And remember that when we've already named f here, we call the antiderivative capital F. And then we, of course, do our constant of integration because we're looking for the general antiderivative. All right, and like I said, and then the U substitution just comes in as sometimes if students have trouble recognizing where their inside function is, that if they look through and they try to identify an inside, you always let your U equal your g of x. Then you take its derivative and put it in differential form, and then you look to see if that is a portion that you can basically take this out and put du in its place, and then it becomes the antiderivative of f of u du. And I apologize, my husband is upstairs tiling the master bathroom, so that's the tile saw going. All right, so the one thing I want to talk to you about is this formal rewriting where I let u equal and then I show the derivative. If you need to do it, do it. But sometimes once we recognize the pattern of the unpacking of the box and then we know we have to put it back in, we don't always have to show that step. So for example, when I look at this problem down here in example 3, I recognize that I have a composition here, and here's the inside function. And then I look and I think, oh, what's the derivative of this? So just in my head, I'm saying, what's the derivative of x squared plus 1? And I go, well, the derivative of this is 2x. And in differential form, it would be 2x dx. And so all of this stuff is essentially going to get packed back up into the box. So what I'm really trying to take the integral of is basically u squared. So in my head, I'm just going, hey, I'm just integrating a power function that has a square in it. So when I integrate a power function, then I know that I'm going to add 1 to the power and then divide. So I do that portion of it. Whatever stuff was in the box comes along, and then I do plus c. And I'm done with this problem and I'm ready to walk away. However, if you have trouble recognizing where your u substitution is, you do want to go ahead and say, in this problem, u equals the inside of the function. My du would be 2x dx, and then we can start manipulating this and realize that where you're taking the integral of u squared du, which is going to be 1/3 u cubed plus c, and then we put our u back in. So whether you need what's written in green or whether you can just recognize by pattern recognition, choose what you need to do. You might want to start by writing the u down. Sometimes I write this part down just because I'm checking, but I don't actually do this portion that I have here in the middle. Once I get the u and the du, then I can sort of see that, oh, I'm just taking the antiderivative of u squared, and so I go u cubed divided by 3 plus c, and then I just write it down. So it's up to you kind of how you want to address this. And practice, practice, practice. All right, now again, here's an example, though, of where you start to see some issues, but it's not going to bother me. Now remember that if I have a constant, all right, that if I were looking at a function and I had the integral of a constant times f of x dx is the same as the constant times the integral of f of x dx, all right? And the other thing that I also want you to recognize is that you can multiply this by any form of 1 you wish. Any form of 1 that you wish. Okay? Now let's see, why am I mentioning this? All right, I'm going to do this one. I'm going to start with u substitution. I scan through this and I realize this has got a 3x and a sign and composition, so I've got some composition going on. So I'm going to identify my inside function as x squared plus 1. I'm going to make my u be the x squared plus 1. And then when I write the derivative of u in differential form, we get that 2x dx. Now what's going to bother us here is the fact that we don't have 2x dx, we have 3x dx. So what we're going to do, okay, and this is our trick that's going to happen, that constant I can pull out. So it bothers me there's a 3 there, so I'm going to pull it out. So the integral of 3x sine of x squared plus 1 dx is exactly the same as 3 times, I'm going to leave a little bit of space here, times the integral of x sine of x squared plus 1 dx. And then when I look up here, I go, I was missing something. What I am missing is this 2. And this is where the trick of we're going to put in what we're missing, but we're going to put it in, we're allowed to multiply by 1. We are allowed to multiply by 1. So I need to have a 2 here so that I have all the stuff I need to pack back up for chain rule. And if I'm going to put a 2 here because I'm strictly required to be multiplying by a form of 1, notice I'm going to stick a constant of 1/2 out here. That if the net that I have multiplied by here is 1, but I have done this in a magic way so that now I can take the antiderivative of this, that now I have the chain rule in the right form so we could pack it up. And if I do the actual use substitution, then what I would see is that this would become 3/2 times the integral of sine of u, and then all of this stuff becomes du. So now I can just go, well, what's the antiderivative of sine? Sine is the derivative of negative cosine. So I would have negative 3/2 cosine of u plus c, and then I put myself back into the correct variable, cosine of x squared plus 1 plus c. Now, the one nice thing about this antiderivative process is once you get what you think is the answer, you can always test yourself out and see if you do end up back with the integrand if you were to take its derivative. All right? Now again, if I was actually doing this problem, and like I said, and this is you learn as you hit practice and kind of moving forward, I pretty much go to this as my second step over here, where I pull out the constant that's bothering me, and I put my form of 1 in, and then from here I directly decide, oh, I know how to do this derivative. I ignore the stuff on the outside, I pack it back up, and then I just take the antiderivative of the sine function, because that's the kind of most important part of this. That's the f that I'm looking at, and I go straight from here to here. So I kind of skip the steps in the middle. They're as unnecessary, maybe clarifying steps, but they're not necessarily something you need to write down. Okay. Now let's take a look at some things about when we do this pattern recognition. Notice that in this case I had an extra constant I didn't need, and I just kind of pulled it out, and it kind of rode along with me all the way to the end. So it was in the original problem. Okay, I'm going to color code. Let's see, what color do we want to do? Let's do this purple. So this one right here was in the original problem. I moved it out, but do you notice that it has ridden along the entire way? It was unnecessary to the integration, but I can't just ignore it, so it rides along. So the constant multiples that are there in the original integrand are going to be called riders. It's not a technical term, but it's going to work for us. So when I say there's a rider, there's a constant that just needs to ride along all the way to the answer. Then we're going to have constant multiples that are generated from the integration rule, like the power rule. Like for example, the fact that we didn't have one in this one because there was no power rule. But if I would have had an antiderivative of u cubed, when I would go to do this antiderivative, you would end up with your u to the fourth 1/4. This 1/4 right here would be called the constant generated by the integration rule. Like when I'm doing the power rule backwards, you have an extra constant that gets added in. So anytime there is a constant that is generated from an integration rule, like for example, when you have b to the x and you're working backwards, you're going to have a constant. When you have a power rule and you're working backwards, you're going to have a constant. So these are called rule constants. So they get added in because you're integrating. And then you've got this third one, which I used above, which are going to be the constants that are going to correct things that are missing. Now these corrections, you can only correct constants. You can't, if you're missing an x and you need an x in there, you're done. You can't do this process on it. But if you're missing a constant, you can correct for that using a form of 1. All right. And so if we are using a form of 1, we just make sure that we put in the constant we wish to have, and on the outside we take out the constant again so that the multiplier of the two of these is going to equal 1 together. So I didn't really change the integral, I just put it in a nicer form. Okay, so we put in the constant we want, we always put the reciprocal on the outside, and that will always be our correction, our constants that are correcting for missing values. And then you just bring your writers along, add in any integration rules that come along, and then use your correction that's coming in, and then that will give us our final answer that we're looking at. All right, and then don't forget at the very end, because we're looking for the general antiderivative, always worth a point, don't forget to do your plus c. That is going to be very important to remember to add in that constant of integration. All right, so let's take a look at this. Let's take a look at example 5, and you can see how these are much more challenging than what we had before. Now the first thing I'm going to do is recognize that I have a writer, that I have a constant that's in this problem that I'm going to immediately just pull out, because it's just confusing things anyway. So we're just going to pull it out and we're going to let it ride along with us. So now I have x and then this x squared plus 1 squared dx. I look at that and I identify an inside function. So I'm going to come along and identify that I have this as my inside function. And typically, like I said, I don't always do this, but I sometimes come over here on the side and I say that's my inside function. My du would be 2x dx, so I kind of do this side work. And then I come over here and I start looking to make sure that I have all the parts of du in the problem for the unpacking part of the chain rule. And what I see is that I am missing a 2. So I go, oh, I need a correction in here. So I'm going to put in a 2, because that's what I need to match my derivative, and then I correct for it with my reciprocal, so that comes on the outside. And now I'm ready to pack everything back up and integrate. So I'm ignoring this right now because that gets packed back inside, and so I'm looking at basically the integral of u squared. Now if you need to write this step in here, please do so. There's nothing wrong with adding it in, 1 over 2 pi integral of u squared du. There is nothing wrong with putting that in and then integrating it using u as your variable of integration. So the antiderivative of u squared is going to be u cubed 1/3, and then notice in addition to a writer and a correction, I now have a constant based on a integration rule, so that 1/3 gets added in. And then at the very end, we go back to our actual variable. So we would end up with 1 over 6 pi, and then my x squared plus 1 cubed plus c. And technically, I should have had a plus c over here. Once you integrate, you've got to have plus c. But it's perfectly fine for you to skip what I have written over here. It's perfectly fine that once you get the correction in there, and you realize that all of this stuff is going to get packed back into the box, then what you're basically doing is going, I'm just going to ignore this. I can like cover this up with my hand or something and say, ignore this, ignore that. I have u squared. What's the antiderivative of u squared? And that's how I get my u cubed and move forward from there. So either way you go, understand how the process of packing it back in is going to work. All right, so let's look at example 6, and let me just make sure, was that the last one on this page? Yep, so now let's go over here to example 6. So now notice that each of these have the same inside function, but they have a different outside function, and since a different rule of integration. And so let's kind of work our way through this and see what happens. So when I look at this, and you know, the one bad thing about this notes is I probably should have put some parentheses in here, but you have 5 sine of 2x, and we'll assume that this is what we meant right there. Okay, so I have 5 sine of 2x and then e to the cosine of 2x. So what you're going to recognize is you got to identify an inside function, and I'm going to identify that as my inside function. So, and again, because we're new at this, let's go ahead and at least write the u down. If I let u equal cosine of 2x, my du is going to be derivative of cosine is sine. Derivative of sine is cosine. Derivative of cosine is negative sine. And then 2x, and then I have a chain rule problem, so I have times 2. So when I'm looking at my problem now, I see that all the 5 is going to be a rider. It's there, it just needs to ride along, but I'm going to pull it out because it has nothing to do with my du. Then I have a correction that I'm going to have to put in. I need to have a negative 2 in front of the sign in order to have the correct du. Let's put my dx. Start not getting into that habit of losing things as we go. All right. So I know that I need to put in a negative and a 2 in order to get this to match. So I add in my correction. I'm going to put in my negative 2, and then I'm going to basically multiply by negative 1/2 over here. It's reciprocal. Then I'm going to fill in the parts that I have. There's my sine of 2x, right? That goes in with my du. We're going to pack that back up. Then we had our e to the cosine of 2x and dx. So really the most important part of what I'm trying to look at right now is really this. The rest of this stuff is going to get packed back up. So I'm going to ignore it. I'm not even going to write it. I'm not going to turn it into a u problem. I'm just going to go right ahead. I can ignore that and move on and say, well, what am I going to have? My antiderivative would be negative 5/2. Bring along your writer and your correction. I'm ignoring this. It gets packed back in. And now I'm going e to the u. What is the antiderivative of e to the u? Well, it's e to the u. So that would be e to the cosine of 2x and then plus c. So as you can see, you kind of work your way with it. If you need to show your u substitution so that we don't make any mistakes, so we can see what we're looking for, go ahead and do that. You can change it completely into u and then take the antiderivative and go back to x, or you can do as I do, which is pretty much, I always show this step, but then I just kind of do the rest of it in my head. All right, now let's look at this one. Now I'm going to rewrite this a little bit just to kind of be a little bit more clear. The 7 sine of 2x is still kind of out here. I'm going to rewrite this as cosine of 2x, and I'm going to put big parentheses around this and make it a 2/3 dx. So I'm going to take a look at this, and hopefully you'll agree with me that the inside function is still 2x. I'm not going to rewrite it again because I have it right over here. So once I've identified that that's my inside function, and I can see that the 7 is a rider, so I'm going to pull that out. I am missing, just like I was over here, the negative 2, so I'm going to add that in. And I'm like the color code here while we're doing this, so I'm going to color code. I'm going to put in my negative 2, and I'm going to take out my reciprocal, so my correction goes in. And then we're going to bring in our sine of 2x. Then we have our cosine of 2x to the 2/3 dx. And again, remember, you are right at this moment ignoring the stuff that you're going to pack back up into the box. This is the box that we're worried about. This is my u to the 2/3. My u to the 2/3. So all I need to do is take the antiderivative of the u to the 2/3. I'm ignoring the stuff everything else because I'm packing that back in the box. And I go, what's the antiderivative of u to the 2/3? Since it's a power rule, we would add 1 to our power, so that would give me 5/3. And then I have a, since I am already doing the antiderivative, let's take that out. I'm doing the integration right now. I add 1, and then I have to divide by the power or multiply by the reciprocal, so I put in my constant from the integration rule, and then I do my plus c. And then maybe if you want to simplify, negative 21 over 10. And if you want to write this back as cosine to the 5th of 2x and do the cube root of it, plus c, you can do that, or you can leave it in your rational exponent notation. That's perfectly fine. All right, let's look at our third example over here. All right, again, I'm going to identify my inside function. I have 2 sine of 2x, and then I have cosine squared of 2x. So again, maybe we should rewrite this. I don't like it when you have the square there, so I'm going to go 2 sine of 2x, then it's cosine of 2x squared dx. So again, doing that's going to make it a little easier to see the inside function, the same inside function that I had in the prior 2 examples. And the nice thing about this one is that the only thing I'm actually missing is the negative. I've got a 2 right here, so that 2's not a writer, that 2's part of the derivative of the inside function. So, but I am missing the negative that goes there. So I am going to put a correction in, put a negative in, put a negative out. And so now I'm ready to go ahead and do the integration. I'm ignoring this stuff here because this is my box that I'm packing everything back up into. And so I essentially I'm going to go bring your negative down, then take the antiderivative of u squared. The antiderivative of u squared would be u cubed, and then bring in your constant from your power rule. And then don't forget your plus c. All right, so hopefully you're starting to see kind of how this is working. You identify your inside function, you identify what you're actually integrating, the u to the 2/3, the u squared, or the e to the u, and you ignore the other stuff. Once you get it corrected so that you can pack it back in the box, then it's ready to go. All right, let's take a look here. Again, what you need to recognize is you got sine of 2x, sine of cosine of 2x. The inside function, let's keep with my color scheme, is this part right here. So it's the same inside function that we had before. And again, hopefully you can see that we're really close. If I slide back up here to my little u substitution notation that I'm using, that I'm missing my -2. So all I have to do is come in, I'm going to put in my -2, and I'm going to take out my -2 with my correction. Then we continue with the stuff that gets packed back up into the box. And then I have my sine of cosine of 2x dx. So the box that I'm looking at is here. All the rest of the stuff I can now ignore. It's going to get packed back in as the chain rule. And I have sine of u. So I go, well, what's the antiderivative of sine of u? Bring your -1/2 down, your constant, your correction. This stuff you ignore. That stuff you ignore. The antiderivative of sine is negative cosine. So times negative cosine, because the derivative of cosine is negative sine. So the antiderivative of positive sine has to be negative cosine of u, okay, plus c. And then if you want, you can just kind of fix your constants, and so we have a negative times a negative, 1/2 cosine of 2x plus c. All right, let's take a look at this one. Now, we might be wondering about this one. Let me take a moment and let's take a look at this function. Now, what's kind of the trick here, and this is where sometimes it starts to get a little bit more challenging, is to recognize you do have an inside, okay? The inside is this portion right here. But the problem I have with that inside function is that doesn't seem to have a derivative that's going to look like this other stuff that's kind of floating around here. So I go, well, maybe there's a trig identity that we might use, that we kind of have to recognize we have a trig identity on this one. So I'm going to rewrite this using the trig identity and kind of pull some things out and kind of rewrite this in a nicer form. So let's take our 2 and our 3. I'm going to just pull those out. I might end up putting the 2 back in. Actually, let's leave the 2 in, planning ahead, because That's probably part of the derivative of the inside function. So I'm going to pull the 1/3 out because I don't think that has anything to do with it. I'm going to bring my integral, which leave some space in case I need some corrections. So we'd have 2 sine of 2x. And then instead of doing a fraction, I'm going to bring this up and make this -1/5 as a power, dx. And then what's inside here, I'm not real happy with this because I don't think it's related to this outside. But I remember that there's an identity that says that cosine squared minus sine squared is actually cosine of 2x. So I'm going to replace this using a trig identity. Trig identity. It's your double angle identity for cosine. So I see that recognition, and the reason why I like this as my inside function is because its derivative has something to do with what's on the outside. Okay, so now we're ready, and we say now we have an inside function. Oh look, it's the same inside function I've had the entire time. So we can tell that we're going to need a correction, that we're missing the negative on the 2 sine of 2x. So I'm going to put the negative in and take the negative out. And now I'm ready to ignore the stuff that gets packed back up in the box. This is the stuff going back in. Here's the box that everything gets packed back into. So now I just need to take the antiderivative of u to the -1/5. Bring your constant along. Ignore the stuff that gets packed away. The antiderivative of u to the -1/5 would be your u. Add 1 to the 4/5. Divide by your power or multiply by 5/4. So there's our integration constant based on a rule coming back in right there. And then of course plus c. So we would have -5/12 cosine of 2x all raised to the 4/5 plus c. All right, and then one more problem that we're going to look at. I'm actually going to show you 2 different ways to do this. In this one, you might be like, well, I don't really see an inside function, but I have 2 of these things going on. Well, the trick is to recognize when you're looking at this that sine of 2x has something to do with the derivative of cosine of 2x. That these 2 things, one is the derivative of the other one. You actually can work this either way, but since we've been doing this with cosine of 2x as our u, we'll just go ahead and we'll leave that as our quote-unquote inside function. Okay, and so we're basically thinking of this as I'm going to pull the rider out 11. So the integral, I'm going to leave a little space here, sine of 2x, and then you can think of this as cosine of 2x to the first. There's nothing wrong with thinking of that as like u to the first, because that's easy to integrate. We see that we're missing our -2, so we put it in and then we put our correction, -1/2. And now we're ready to do our integration. We recognize where our box is. So the box is going to be u to the first, And so all we have to do is bring along our constants. So I'm going to have -11/2. Ignore the stuff on the outside, it gets packed back in. So I have u to the first, which would be u squared, and then divide by 2, so multiply by 1/2 plus c. So my final answer, -11/4 cosine of 2x squared plus c. So that's one way of doing the problem. Another kind of method of doing this problem, you could decide to make your inside function, make the u sine of 2x. It actually works pretty much the same way. I'll leave that for you to verify that if I make my u sine of 2x, that you'll get the same answer. Okay, so that is kind of this idea, giving you a good overview of your kind of packing it back in, taking your chain rule and packing it back in. So I'm going to stop this video here, and I believe I'll pick up the rest of the examples in a second part because this is going to play around with some of the trig antiderivatives a little bit more.